This video gives you a superpower, okay? We can say tons of things about critical points without even seeing them. So let's start off with it. But again, the goal for this video is to answer this question. If we find a critical point without a graph, how could we find out whether it's a max, a min, or neither? Well, let's start off with another question. Example 5. What can you say about the derivative of the following graphs around each critical point? I'm going to shade it in different colors. Well, around the critical point, notice it's increasing on the left at this maximum, and then it's decreasing to the right. That's not a coincidence, right? Because if the max is the biggest around, then it should kind of go down from both sides. So if we read left to right, that means we should be going up the hill and then down the hill. And for minima, right, it should be the opposite. We should be going down the hill and we get to the bottom and then we have to go up. Is that going to be true for all of these extrema? Again, this maximum is going up and then going down. Yeah, that's a local max. This minima is going down and going up. And notice that this is a different kind of maximum than this, right? There's two different kinds of critical points. The one on the left has a horizontal tangent line, and the one on the right is a critical point because the derivative doesn't exist. Well, it works for both of them. And same the minimum, both kinds of minima. It's going down on the left and then going up to the right. Positive and negative derivatives. And over here, this is also a critical point. But in this critical point, notice it's going up on the left and up on the right. So it's a critical point, but it's not an extremum. And over here, right, it's going down to the left and down to the right. It's a critical point, but no extremum. Okay. This is basically the first derivative test. So max, right, is increasing and then transitions to decreasing. The minimum at a critical point was decreasing and then transitioned to increasing. This makes sense, right? The minimum's the bottom of the valley. You're going to go downhill and then you start going uphill. That's the first derivative test. And again, if you just increase, that's nothing. That's just a hike with Jason. It's always uphill. And then if you just decrease and then decrease, again, that's not a hill or a valley. You're just going down a different kind of hill. This is a visualization of the first derivative test. So let's introduce it. Suppose we have a critical point. We can classify that critical point using derivatives, the first derivative specifically. So if the first derivative changes from positive to negative, right? Positive derivative means positive slope. Negative derivative means negative slope. Well, if we're going up and then down, what kind of extremum do we have? A local max. And similarly, if the derivative goes from negative, downhill, to positive, uphill, then we have a local minimum. And if it doesn't change sign, so if it goes like uphill and then more uphill, or downhill and then more downhill, well, there's no local extremum there. No local max and no local min. That's the first derivative test. We can look at it in a couple different ways. We'll introduce it with this example, and then we'll do a more typical example in the next video. Suppose our function, example 6 now, suppose our function has critical points where x equals 1 and x equals 3. So again, we can visualize that on a number line. We have critical points right here. Let's label these. This is the location of a critical point. Again, a critical point is an x and y value, but this is where a critical point can occur. And we found that the derivative at 0 was positive. So f prime, the derivative, the slope, was positive here. It's going up. The function's going up right here. And we also found that f prime of 4 was positive, right? The function's going up right here. We found that f prime of 2 was negative. That's telling us the function's going down right here. Classify the critical points. Classify this point right here and this point right here. Well, we can use the first derivative test. The critical point, where x equals 1, what is that? Well, it's going up, and then we're going down. That's a local max. Similarly, the critical point at x equals 3, well, it's going down and then going up. There we go. It's a local min. Technically, this logic does require continuous functions. Otherwise, you can get weird things without continuity, but we'll mostly be dealing with continuity for this stuff. There we go. That's it. That's the first derivative test. We'll be remaking this chart in future problems. The next video's got a longer one where we actually have to do all the work, most of the work ourselves. We revisit that old function that we graphed over here, that we graphed over here, and we'll use the first derivative test on it. All right. Let me know if you have any questions, and bye-bye.